In the previous video, I showed you the three types of deviations that we can calculate to help us better understand the score on a response variable when we are modeling that response variable as a function of an explanatory variable. In this video, I will show you how to use R to calculate these different types of deviations. I am going to use the MT-CARS dataset. I begin by loading these data. The dataset contains many variables, and I just want to focus on horsepower and engine displacement. So I'm going to pull these two variables out of the dataset. Here's an interesting little tidbit about R datasets. You can give each case in the dataset a name without using an object variable. R calls these row names because, of course, every row in the dataset is one unit of analysis. There are ways to embed the names of each unit within the object without creating a variable for that name, and the author of the MT-CARS dataset has done that. I'm going to pull those names out of the object using the row names function. As you might guess, when we use the data object as a parameter for the row names function, the function will tell us the names of the units. Rather than display these, I'm going to store these in a variable that I have chosen to call name. We're going to focus on the power of the automobiles as the response variable and the size of the engine as the explanatory variable. The total deviation of the response variable score is the distance of that score from the mean of all the response variable scores. I'm going to calculate the total deviation for power measured as horsepower by subtracting the mean horsepower from the horsepower for each of the individual cars. The other types of deviations rely on our model. We want to use a linear model that relates horsepower to engine size, defined as engine displacement in cubic inches. I'm going to use the LM function to create this model, and I'm going to store the results of this function in a new object that I am calling lm.hpdisp. Here's something cool. When we run the linear model function, it calculates the predicted values and the residuals for our response variable. These are now stored as variables in the object. R calls the predicted values fitted values. R creates a new variable for these called fitted.values. R creates a new variable for the residuals that is simply called residuals. To make life easy, I'm going to pull these variables out of the object and store them in variables that I am calling predicted and residual. The model deviation is the difference between the predicted score that will land right on our regression line and the mean. I'm going to create the model deviations. The error deviation, which is also called residual, has already been created for us. Thus, I now have all three types of deviation scores. I'm going to create a new data object, which I'm going to call r.data. And I'm going to bind all the variables that are of interest to me into this object. To do this, I'm going to use the cbind function, which is short for column bind. The variables in my new object are, in order, the name of the type of automobile, the engine displacement, the horsepower of the automobile, the predicted horsepower when modeling horsepower as a function of engine displacement, the total deviation of power from the mean, the model deviation, and the residual. Let's look at our data. One of the primary reasons for creating a model is that it can help us better understand each individual unit. Here is the car that I focused on in the previous video. It is the Ford Pantera L. This car has an engine displacement of 351 cubic inches and power of 264 horsepower. That's a big engine. So we would predict horsepower that is above the mean horsepower for all the automobiles in this data set. Specifically, we would predict 199 horsepower for the Ford Pantera L. The actual horsepower is 264. This value is 117 above the mean. We can explain about 53 horsepower of this deviation based upon the engine size. We cannot explain the additional 65 horsepower. What is the residual telling us about this automobile? It is telling us that we are getting more horsepower than we would expect for that size engine. This tells us something about the engineering of that car. Studying the residuals of different automobiles helps us better understand something fundamental to the automobile. What type of outcomes are achieved because of the engineering of the car? Scan the residuals in our data set. Here's one that just pops out at me. This is about 158 horsepower, meaning that this automobile, the Maserati Bora, achieves 158 more horsepower than we would have expected for the size of the engine. The engine is 301 cubic inches, so we would have predicted horsepower of 177. But instead, the Maserati Bora has a horsepower of 335. This is remarkable, and I want to know what's going on with the engineering of this vehicle. Let's look at the other side of the spectrum. Scanning the residuals, I notice this one of -46. This is the Pontiac Firebird. It has a very large engine with a displacement of 400 cubic inches. I would predict 221 horsepower with that size engine, but we only get 175 horsepower. That's 46 less than we predict. What is the purpose of this big engine if we only get 175 horsepower? I hope that you're beginning to understand that the calculation of statistics for a variable using a group of units of interest is not just about understanding the characteristics of the entire group. That is a first step, but once we better understand the characteristics of the group, such as when we look at central tendency, or when we model a response variable as a function of an explanatory variable, we can use that information to better understand the characteristics of each individual unit. The car's example is just one example. We could think of many others. In the education domain, we know that the standardized test scores of students in a school are related to the socioeconomic status of the region that is served by the school. That is because socioeconomic status is itself related to a variety of variables, such as parental education, school resources, the education and experience of the teachers, and so on. Suppose we were to build a model that relates the average student standardized test score for some test to the socioeconomic status of the region. Our model would almost certainly reflect that higher test scores come from higher SES regions. But what if we took it a step further? What if, for example, we look for a school with a low SES that has a high residual? If you were an education researcher, seeing that residual might prompt you to go look at that school to see what is going on. How is a school with low SES able to achieve these kind of student outcomes? I could provide many more examples, but the main take-home message I want to leave with you as we finish this video is that statistical analysis is not just about the study of a group. That's a common misconception that I frequently hear and that I do my best to address. But it's sometimes difficult to convey how the calculation of group statistics and linear models can lead to better understanding of individual units. It's much easier to convey this when we carefully take the time to walk through the steps of analysis. That is what you have been doing, and I hope that you feel amply rewarded for taking the time to do that, and that you're motivated to continue your learning. I look forward to assisting in that process.